This video is for section 13.1 about the nature of gases. Learning goals are to be able to understand assumptions made in the kinetic theory of gases, to understand how the kinetic theory explains gas pressure, and to understand the use of Kelvin temperature to measure average kinetic energy. Let's take a look at that first learning goal. Understand some assumptions made in the kinetic theory of gases. Kinetic energy is the energy an object has because of its motion. There's a theory called kinetic theory. It says all matter consists of tiny particles that are constantly moving. When relating the properties of gases to the motion of the gas particles, the following three assumptions are made. Gas particles are small, hard spheres with insignificant volume. Gas particles are moving rapidly, randomly, and constantly. And collisions between gas particles are perfectly elastic. In reality, the particles that make up different gases, for instance, the gas nitrogen, the gas oxygen, or mixtures of gases like air, are not spherical in shape. If you think about the atoms that bond together to create different gases, you know that they're not spherical. Likewise, we know in reality that particles of gas have a volume. Because they're made out of actual atoms, that's going to take up space. But for purposes of studying gases, we're going to assume that they are spherical shaped particles and that they have practically no volume at all. Because gas particles are constantly moving, they can collide with each other. And we will assume that the collisions are perfectly elastic. What that means is that no energy is lost when the particles bump into each other. They just smack into each other and then head off into new directions. The next learning goal is to understand how the kinetic theory explains gas pressure. Gas pressure is the force exerted by a gas against an object due to the gas particles colliding with the object. Think of a balloon and blowing air into the balloon. The force of the air particles that your breath puts into the balloon presses against the inside of the balloon and expands that balloon. Or think of the pressure of the air that's put into a tire on a car. The particles of air in the tire press against the inside of that tire, and that's what keeps the tire inflated. A vacuum is empty space that contains no matter. Because there are no gas particles to collide with objects in a vacuum, there is no gas pressure in a vacuum. One type of gas pressure is atmospheric pressure. This is the force exerted by air molecules against objects on Earth. You can't feel it, but all the air above you right now is pressing on your body and exerting force. The reason that you don't feel that pressure is that there are equal forces in your body pressing out, and those forces are in balance with each other. A barometer is a device that measures atmospheric pressure using one of the following units of measure. Atmospheres, ATM. Millimeters of mercury, mm, Hg. And kilopascals, kPa. All three of these units of measure are used to measure atmospheric pressure. Here are the equivalencies. 1 atmosphere of pressure is equal to 760 millimeters of mercury, which is equal to 101.3 kilopascals. In this chapter, we'll encounter a concept called standard temperature and pressure, which is abbreviated STP. Standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere. Here are some check for understanding questions. I'll pause the video for you to answer these, and then we'll discuss before continuing on. And here are the solutions. The atmospheric pressure in Bridgeport is greater than the pressure at the top of Mount McKinley, Alaska. And the reason is there's more atmosphere above us in Bridgeport. Number 2, convert a pressure of 320 millimeters of mercury into atmospheres and into kilopascals. So our first conversion, you write down that given number, 320 millimeters of mercury, then multiply by the conversion ratio. Because this unit was millimeters of mercury, we want that to be in the bottom. And the unit we want to convert into, atmospheres, we want in the top. On the calculator, go 320 divided by 760. And the result is 0.42 atmospheres. For the second question, we're also beginning with 320 millimeters of mercury, and we're converting it into kilopascals. So on the top, we want the 101.3 kilopascals. And this rounds to 43 kilopascals. Here's the next learning goal. Understand the use of Kelvin temperature to measure the average kinetic energy of particles. The particles of a substance are in motion, so they have kinetic energy. Some of the particles may have less or more motion, and therefore have less or more kinetic energy than others. So it is typical to describe the average kinetic energy of all the particles in a substance. When we talk about a substance having a temperature, temperature is a measure of the average kinetic energy of the particles in the substance. We know that there are different scales to measure temperature: Fahrenheit, Celsius, and Kelvin. And in chemistry, we will most often use Celsius or Kelvin. The Kelvin temperature of a substance is directly proportional to the average kinetic energy of the substance. For example, a substance at 100 Kelvin has twice the average kinetic energy of a substance at 50 Kelvin. Here's another example. A substance whose temperature is 500 Kelvin has 5 times the average kinetic energy of a substance at 100 Kelvin. If you were to use the Celsius or Fahrenheit scales to measure temperature, then temperatures are not directly proportional to the average kinetic energy. It's not as easy to compare them. So in this chapter, we'll use Kelvin temperatures a lot. Here's a reminder of the temperature conversion formulas that we saw earlier this year. A Kelvin temperature is equal to the Celsius temperature plus 273. If you ever needed to find a Celsius temperature, it's equal to the Kelvin minus 273. This concludes the first lesson in Chapter 13, in which we're going to study properties of gases. Properties that were introduced in this video were the concept that gases have pressure and that the Kelvin temperature scale is the best one to use to measure the temperature of gases.